அதான் நம்ம உட்காந்து பேச முடியாது. அந்த டாக்குமெண்ட்ஸ் பார்க்கணும். இவன் போன் பண்ணிட்டே இருக்க காலையில இருந்து. அந்த பூஜை நம்ம 92 93 தான் பார்த்தோம் இல்ல, 89 87 88 89 அந்த வீடு, 90 போஸ்ட் வேண்டாம், எலக்ட்ரிக் போஸ்ட் வேண்டாம், 90 91.
சார்
4 பேர் வந்துட்டாங்கல்ல.
ஓகேங்க சார். ஓகேங்க சார். சார் ரெக்கார்டிங் ஆரம்பிச்சுக்கலாம் இல்லைங்க சார்? ரெக்கார்டிங்
ஸ்டார்ட் பண்ணிக்கலாம்.
ஓகேங்க சார். ஆகாஷ் ஸ்டார்ட் பண்றியா?
நான் ஆரம்பிச்சு விட்டுறேன், அப்புறம் ஸ்டார்ட் பண்ணிக்கங்க. ஓகே
சார். சரிங்க சார்.
ஓகே. So good afternoon to all. On behalf of Max Department as the HOD, I welcome Dr. Nirmala Area Madam for giving this webinar under IIC. I am hand over to the session to Dr. Shanbag Madam as a coordinator. Okay, madam, carry on.
Okay, sir. Sir, master of ceremony going to proceed. Akash, sir. MC.
Okay. Okay.
So greetings of hope in the midst of COVID-19 pandemic. I'm very happy to see you all through the online platform for this webinar on fascinating dimension on natural fractals. So I'm Akash. I'm going to do the MOC for the whole program today. So let's move to the program. Prayer is the best way to find ourselves and get ourselves into the hands of God. So it's better to start this webinar with a prayer song. So for that, I invite B. Srimati to offer a prayer song, please.
வேண்டும் வரங்களை இசைப்பேன் கேளாய் கணபதி, எனக்கு வேண்டும் வரங்களை இசைப்பேன் கேளாய் கணபதி, மனதில் சலனமில்லாமல் மதியில் இருளே தோன்றாமல், மனதில் சலனமில்லாமல் மதியில் இருளே தோன்றாமல், நினைக்கும் பொழுது நின் மௌன நிலை வந்திட நீ செயல் வேண்டும், நினைக்கும் பொழுது நின் மௌன நிலை வந்திட நீ செயல் வேண்டும், கனக்கும் செல்வம் உருவயது, கனக்கும் செல்வம் உருவயது, இவை இவை எனக்கு கேட்டும் வரங்களை இசைப்பேன் கேளாய் கணபதி.
Thank you for giving a wonderful start by offering a great prayer. Moving on to the next part of the webinar, welcoming is the most important part of our tradition. So we have to welcome all gathered here. So for that, I request S. Deepak Kumar to offer the welcome address.
Hi and hello to everyone. A warm greetings to one and all present here. It's a pleasure to meet you all in this present evening. Myself, S. Deepak Kumar from the Department of Mathematics at PhD College of Arts and Science. It's been quite a short time for each and everyone during this extending pandemic. Yet, we are all here as upcoming mathematicians who's determined to find solutions to every problems and fighting forward towards our every goal every day. Now, proceeding with our program, I feel great to welcome Dr. D. Gunasegaran, the head of our department, and Dr. K. Shanmugam, the coordinator of this webinar, and all the other valuable faculties of the department. And on behalf of our entire department, I feel honored to welcome Dr. F. Nirmala Idudayam, Assistant Professor from the Department of Mathematics of Nirmala College for Women, who is here to enlighten us with her ideas on fascinating dimensions of nature fractals. Welcome to our department, ma'am. It's a pleasure to have you with us. And last but not the least, I feel obliged to welcome my fellow friends and seniors, the students of mathematics department who are enthusiastic of what's about to be happened. And also welcome to those of you just joining us. So without any regret, let's set up with this session. Thank you, one and all.
Thank you. Great welcome address. That welcome address will give us some energy to moving on to the next part. All Vedas say when you are learning something, it's equally important to learn about the Guru who is going to taught something to you. So in that part, here comes S. Kailash to tell us a brief introduction about our speaker and chief guest, Dr. F. Nirmala Idudayam.
Good evening, everyone. On this occasion, I am glad to welcome our chief guest, Dr. Nirmala Idudayam, who spent most of the days in her life with mathematics. This is not an exaggeration, as she published 54 papers and authored a chapter named Bipolar Neurosophic Cubic Graphs and its Applications in the book called Handbook of Research on Advanced Applications of Graph Theory in Modern Society. These are a tip of iceberg, as her achievements also include supervising 3 MPhils and a PhD along with working on 4 other PhDs. Through her academic wit, she has an experience of 18 years in teaching and 9 years of researching. Now the symbol of dedication and an inspiration for budding mathematicians is here to preside our webinar on fractals. Without much delay, let me welcome Dr. Nirmala Idudayam on behalf of the students and the Department of Mathematics aided PhD College of Arts and Science. Welcome, ma'am.
Thank you for to introduction about the speaker. So we're thinking that we are having a great person with us today for this great evening. So it's time to hear some great knowledge of voice. So I'm inviting Dr. F. Nirmala Idudayam, Assistant Professor of Mathematics, Nirmala College for Women, to take the floor and give us some wisdom.
Can I start with my presentation? Can I share my screen?
Sure, with pleasure.
Thank you. Can you see my screen? Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Thank you. Thank you. So at the outset, let me first thank the principal, the management, the faculty members of the Department of Mathematics aided, the members of the Institutional Innovation Council for having given me an opportunity to be a part of the ocean of activities conducted by one of the premier colleges in Coimbatore, the PSG College of Arts and Science. Thank you very much. And I especially thank Dr. Mrs. Shenbagam, who has invited me for this webinar. And in this occasion, I place on record my sincere thanks to the management and principal of my college, Nirmala College for Women, who always motivate our endeavors. And going straight into the topic, today's topic for the webinar is a fascinating dimension of nature. So we will be seeing about fractals in this webinar. Can this be an interactive session, dear students? Can I ask you general questions? If you permit me. If you permit me, I'll ask you, otherwise, no issues.
Students?
It's not
Yes,
going
ma'am.
It's not going to be tough.
Yes, ma'am.
Just for the sake of interaction. All right, thank you. So in that case, can anyone tell me the shape that you relate with a cloud? All of us have seen the cloud, right? We've seen clouds, mountains, the coastlines, that is the rivers, all these things. Can you relate any shape to these?
Shall I answer, ma'am?
Yes, please. Yes, please. You're welcome.
I think it's different from time we see. Sometimes it may be shown as something, and some animal or some pictures, but
Okay.
it may differ from time to time.
Very good, very good. Normally, when you were very young, when might be in your school, primary school days, how would you draw a cloud?
Like an extended flower, ma'am.
You will draw it like a flower or a circle, right? Okay. And since we are in, and how do you draw a mountain? How do you visualize
Like a triangle.
Yes?
Like a triangle.
Like a triangle, very good. So these circles and triangles are for two-dimensional, all right? But we are in the real world. Any real world object will be of what dimension? Of what dimension? 3 dimensions. So a circle will now be mapped onto a sphere, and a triangle in that case will become a cone. Right, very good. Beautifully said. And yeah. So there was one person called Benoit Mandelbrot who said, clouds are not spheres, mountains are not cones, coastlines are not circles, a bark is not smooth, nor does the lightning travel in a straight line. So these lines of this person made me think, because we've always been thinking that clouds are almost spheres, mountains, when we think of mountains, we think of cones, but he says they are not the same. Okay, so for this, let us find out the answer in this webinar. Okay, now the next one is, we will move into the layman definition of what a fractal is. A fractal is a rough or a fragmented geometric shape that can be split into many parts, and each of the smaller part is a reduced size of the original one. Okay, and then the non-regular fractals appear the same at different scales. You know what scales are? Measurement, the ratio in which we measure, okay? And then the fractals can also be told as never-ending patterns, and they can be created by repeating a simple process over and over again, okay? See, if you can see the figure, can you see the figure or the diagram on the other side? Can you see?
Yes, ma'am.
Yes. So you can see that you can see that all this part is similar to this part, and this part is also similar. All right. So you always see that they are the smaller parts of the original one. If this is the original picture, if I take this smaller part, that will resemble the whole part of it. Okay. So this is the layman representation of the definition of fractals. But since we are mathematicians, we'll also have to give the mathematical definition of fractals. So now let us see what the fractals are in mathematics. They are infinitely complex repeating patterns that are same across different scales. So when I say this, we literally mean the concept of self-similarity, okay? Being similar to the self. And this word complex, this complex comes because of the recursion, the process of recursion. You've already studied what is recursion equations, all that in many of the mathematical subjects. So here, what do we repeat on and off is a simple method. You will be repeating a simple method on and off so that it becomes a complex structure. And the important thing here is fractals are subsets of the normal Euclidean space. And whenever there's a Euclidean space, we always connect a dimension with it. And these fractals have got a fractional dimension. And this fractional dimension is strictly more than the topological dimension that we normally do. All right? Now, these fractals can be broadly categorized into two. One is naturally occurring fractals, or the natural fractals, which can be seen in nature. And the other one is abstract fractals, which can be visualized using the help of computer graphics. Okay, so as examples of natural fractals, you can see that the trees, the rivers, coastlines, mountains, and all these, see the feathers of the peacock, the broccoli that we eat, all these are similar to each other, and therefore they become fractals. Say, for example, this part, if you take the whole part is also similar to a subset of this. Similarly, the broccoli, the parts of the broccoli are similar. And all these are not man-made, they're all natural. And coming on to the next one, the abstract fractals. These, as I told you, they'll be generated by a computer which calculates a simple equation. It's not a complicated equation. It will be a simple equation. And that equation, if you calculate it on and on, you get abstract nature, and that's called as the abstract fractals. And the figure that you see on the top is called as the Mandelbrot set, and here this is called as the Julia set, and these two are very famous abstract fractals. Okay, now once we know about the concept of fractals, the first question is, who got this into the world? Yaar in the fractals ella kandupidichanga? Modalla andha kelvi varum. Okay, so going on to the history of fractals, we say that it came from the Latin word called fractus, which means an irregular surface line that can be broken. And that broken line is similar to that of a stone. Can you visualize a broken stone? How will the broken stone be? Will the edges be smooth, regular?
They will be sharp, ma'am.
And that will be sharp, it will be irregular. Shanbugam, ma'am, ma'am?
Yes, madam.
Bilingual irundha paravalingla?
Okay, madam. Okay, no problem, madam.
Okay, so thank you, ma'am. So it is an irregular surface line that can be broken into small pieces, and it will have some sort of irregularity associated. And the first fractals was discovered by a French mathematician called Gaston Julia. And his discovery was decades before the computer graphics was invented, okay, or before the advent of computer graphics. So when he discovered, no one understood, or he could not clearly explain, or many people could not clearly visualize this concept, all right, the concept of recursion and the concept of irregularity. So years later, the same concept was rediscovered by this person called Mandelbrot, okay, Benoit Mandelbrot, who was a student of this Julia. So this Benoit Mandelbrot is known as the father of fractals. And if you remember, this is the Mandelbrot set. So this is the famous Mandelbrot set, okay? Now moving on to the next one. Whenever we say there is a new invention, something new that's happening, when do we say that there's something new? Or when is the necessity that you need something new?
When we have a need.
When we have a need. Right, very good. Then when there is some flaw in the earlier existing pattern, or existing thing, we need something new. For example, your dresses have outfitted you. There'll be a reason for something new, right? So when we talk about shapes, conventionally we used only Euclidean geometry, all right? So those shapes were regular objects. When I talk about circles, triangles, all these things, they are regular objects, and always there is a smoothness associated with that object. So those shapes were studied under Euclidean geometry. That is, like triangles, circles, the volumes of cylinders, spheres, arcs, whatever it is. Okay, but then there was a time when, as I told you, I showed you the slides where there were irregular patterns which occur in nature. So when there are irregular patterns in nature, how do you study it using this Euclidean geometry? So this was a challenge at that time, and because of that, we had the introduction of the fractal geometry. So what happens, whatever was a disadvantage of the Euclidean geometry has now become the advantage of fractal geometry. It means that Euclidean geometry was not able to study about irregular objects, but fractal geometry could study about irregular objects. Euclidean geometry can only study about smoothness of an object, but nature is full of roughness. Okay, so that roughness could be studied with fractal geometry, and the randomness in nature, that is, as time moves on, as there is a span of time, nothing remains the same, right? So there is a randomness, and this randomness can be best studied by this fractal geometry. And therefore, there was a birth of this new subject. Any doubts till this? Can I continue? Can I? Yes. So as I told you, this Euclidean geometry would differ from fractal geometry by two aspects. One is the shape, and the other one is the dimension. So when we talk about dimension, there are two classical ways or conventional ways of describing this dimension. That is, to define dimension, you need the number of coordinates of the system. For example, if you need to specify where you are standing in a room, you will have to allocate the distance from the x-axis, or the length, breadth, and the width. All right. So you need coordinates. All right. But for natural systems, these coordinates are different. Okay. And all of us know that in classical geometry or the conventional Euclidean geometry, points are of 0 dimension. Lines and curves, they take one dimension of 1. It is of 1 dimension. And squares, circles, they are of 2 dimension because they are plane figures. And cubes, cylinders, spheres, they're all of 3 dimension. Agreed? Yes or no? Yes or no?
Yes, ma'am.
So they have, if you could see, all these are integer values, 0, 1, 2, 3. So all the dimensions are integer values. But that all these are because of the smoothness of the object. But here, when I talk about fractal geometry, I told you in the earlier slide that there's some sort of a roughness connected with that. So the dimension will not be an integer. It will be a dimension between any 2 whole numbers. All right. So will you have an integer value between any 2 whole numbers? I'll tell you, it will be a fractional value. Okay, it will be a non-integer value, and therefore the fractional dimension is always a non-integer, and fractional dimension is always for irregular objects. Now, when we spoke about dimension, the conventional way of describing dimension was D is equal to log of n divided by log s, where s represents the scaling factor, and this is always a natural number, and n will represent the number of smaller self-similar figures which is needed to create the larger one. So just keep this definition in mind, and now we will see how we are getting the dimension for the Euclidean geometry. So to find out the dimension of a line, this by the earlier given formula, D will be equal to log of n divided by s, where s is the scaling factor. So scaling factor meaning this line A is now scaled, scaled another time, meaning there are 2 lines. So s becomes 2. And what is n? The number of self-similar. And என்ன இருந்ததோ அதே மாதிரி செல்ஃப் சிமிலரா எத்தனை குட்டி குட்டி செக்மெண்ட்ஸ் இருக்குன்னு பாக்குறோம். எத்தனை இருக்கு? B1 இருக்கு, C1 இருக்கு. எதுக்கு சிமிலரா இருக்கு? Aக்கு சிமிலரா இருக்கு. So you can so there are 2 self similar things. So you will have log 2 divided by log 2, which will give you log 1. This is how we say the line is a one-dimensional. Similarly, you can just go through the dimension of a square. The square, we say the dimension is 2. So here, this is how you get 2. And for the cube, we say it is 3, and this is how you get the dimension of the cube to be 3. All right. So here you can see the bigger cube is it is 3 times. If you measure the length, it is 3 times of the original one. So it is S is 3. And n will be 27, and therefore you get 3. All right? All right? So this is how we conventionally define the dimension. Now, going back to the fractals, what are the characteristics of fractals? Adoda or தனித்தன்மை என்ன அப்படின்னு பார்க்கணும். என்ன அது எப்படி இருக்கும் அப்படின்னா, it is a fine structure. எப்போ ஃபைனா இருக்கும்? Small structuresல பார்க்கும்போது it is fine. Okay, so whenever you see here as small structures, they all look the same. Okay, and the other concept is they are too irregular to be described in the traditional Euclidean geometry. So Euclidean geometry cannot define fractals. And another important feature is the concept of self-similarity. And as I told you earlier, this fractal dimension or the Hausdorff dimension is always greater than the topological dimension. The topological dimension is what we did earlier. And the important observation is that the fractal dimension or the Hausdorff dimension will always come out to be a non-integer dimension. And all these fractals occur because of the recursive property of simple equations. All right. So these are the concepts that you have to know. The next one is the properties of fractals. So once we know what is the concept of fractals, its definition, and the characteristics of fractals, you can see what properties they would have. That is, they have three properties, important properties, I could say they only have self-similarity, and then in self-similarity, there are many types. One is the exact self-similarity, the other one is quasi-self-similarity, and then the statistical self-similarity. Now, what is exact self-similarity? So the exact self-similarity is the strongest type among the three, and here the smaller parts look identical even at any number of scales, different scales. And these fractals can be defined by iterated function systems, and they often display exact self-similarity. So examples for exactly self-similar structures would be the Sierpinski triangle, the Koch snowflake, the fern leaf. See, if you can see the fern leaf, this is the whole leaf, but each part is made up of self-similar. This is similar to this one, and this is again similar to the whole thing, okay? And it is exactly self-similar. You cannot find any difference between the whole thing and a part of it, a frond of it, okay? So this explains exact self-similarity. And the next similarity, can I get an answer? What will be the next self-similarity? What was the next self-similarity? It was quasi-self-similarity. So quasi-nale ஒரு பார்ட் ஆஃப் இட் அப்படின்னு தான் சொல்றோம். எதோட பார்ட்னா செல்ஃப் சிமிலாரிட்டி முழுசா இருக்காது, ஆனா கொஞ்சமா இருக்கு. A looser form of self-similarity. So here the fractals appear approximately identical, not exactly, okay? Approximately identical at different scales, and they contain small copies of the entire fractal, but in distorted and degenerate form. And the fractals defined by recursive relations. So there it was because of the IFS. Here it is because of the recursive relation. And these, if you form fractals using recursive relation, then it is usually quasi-self-similar. All right. And an example, best example is the Mandelbrot set, which is quasi-self-similar to itself. As the satellites meaning the projections here. The projections are approximations of the entire set, but not the exact set. Here you can see how computer graphics can be used to form the fractal images of the father of fractals, Mandelbrot. Can you see? Can you see this?
Yes, sir.
Okay. Now the third one is statistical self-similarity. So this is the weakest type of self-similarity and has numerical statistical measures that are preserved across the scales, and random fractals are examples. The first one was because of the IFS. The quasi-self-similarity is because of the recursive function. Now here it is something random. Random fractals are examples which are statistically self-similar, but not exactly or quasi-self-similar. அந்த ரெண்டுலயும் எது ஃபிட் இன் ஆகலையோ அது வந்து இந்த statistical self-similarity-ல ஃபிட் ஆயிடும். So an example is, you can see the root structure here. The whole thing is not, part of it is not similar to the whole thing, but it is statistically, you can say, yes, it belongs to this family. All right. So similarly, this coastline of Britain, this was one of the reasons why there was the origin of fractal theory. So இங்க என்ன ஆச்சு அப்படின்னு சொன்னா, இந்த பிரிட்டன், இது பிரிட்டன், கிரேட் பிரிட்டன், இந்த கிரேட் பிரிட்டன் வந்தோட கோஸ்ட் லைனை மெஷர் பண்ணணும் அப்படின்னு சொல்லி ஒரு டாஸ்க் கொடுத்திருந்தாங்க. அப்போ ஒரு சில பேரு ஒரு ஸ்கேல் ஆஃப் மெஷர்மெண்ட் எடுத்து they started measuring it like this. Okay, if you could see the first figure here. So do you think, and they gave them a measurement, do you think that would be the exact measurement?
No, ma'am.
Okay. Why?
Because of its irregular shape, ma'am.
Because of the irregular shape, yes. See, here, these parts are not in Britain at all. These parts are not in the area of Britain at all, but then they are measuring it. You cannot measure. That time they could not measure all these smaller scales, all right? So this was not exactly the area of Britain. So what they did was they reduced the scale size. All right. So when they reduced the scale size, again, they started measuring along the coastline. But even then, what happened, you could see that certain parts, it was not as bad as the previous one, but then certain parts were left. Some parts which were not there in Britain's coastline was included. Some parts which are actually there as a region are left out. See, these are the parts which are left out. These parts which are not are not in Britain, they were included. So this did not give the exact the length of the coastline there. So again, they reduced the scale. So when they reduced the scale, now almost, do you think they would have got the correct results? Almost similar results?
Approximately, they would have got.
Yes, because the area which are left out is very, very negligible. And you know, coastlines are liable to change. நம்ம கடற்கரை பகுதி எல்லாம் வந்து எரோஷன் இருக்கிறதுனால கண்டிப்பா ஒரு அளவுக்கு கண்டிப்பா அந்த சேஞ்சஸ் இருக்கத்தான் செய்யும். ஸோ அது எல்லாமே வந்து ஸ்டாட்டிஸ்டிக்கலா தான் நம்மளால மெஷர் பண்ண முடியும். All right. So this the measuring of the coastline of Britain was one of the reasons why fractal theory also came into existence. Now, moving on to the next one. See, this is the Mandelbrot set, and this Mandelbrot set, if you're going to zoom a particular part, this is how it will be. Again, if you zoom it, this is going to be the part. And here, as you keep on zooming, you see everything seems to be the same. There's no change. And this is what is mathematically called as the concept of self-similarity. So when you talk about fractals, the important thing that you have to remember is only two. For your stage, it is going to be only two. That is self-similarity exhibited and then the non-integer dimension. These are the two things that you have to remember if you're going to talk about fractals. Now, going on to the lighter side of it. Now, do you think these two pictures are the same? Are these two pictures the same?
Yes, ma'am.
Yes. When do you say this? How many say no? All of you agree that these two are same? I think, was it Akash and some other girl who answered?
Akash and Sneha.
Okay. As Akash and Sneha told, these are the same pictures. The only difference is because of the color. And you know, this is nothing but the Mandelbrot set that I told you. This was the Mandelbrot set, which I gave you in the previous slides. And these two sets, they are the same. See, they are the same. And the only difference that comes is because of the color, choice of the color. And now, moving into the special types of fractals, that is, we are coming into the mathematical part of it. So these fractals can be developed in two ways. Number one is a complex number fractal, or it can be an iterated function. That's what I told you as IFS, iterated function system. All of you are familiar with the concept of complex numbers? Are you all familiar with the set of complex numbers? All right. So complex numbers, you know, there is going to be an imaginary part associated with that number. So any complex number in the complex plane, Z, can be written as A plus IB, where A and B are integer values, and I is the imaginary part of it. All right, and I is equal to square root of -1. So using that concept of complex numbers, we are going to make fractals, and the best examples for complex number fractals are Mandelbrot set and the Julia set, and these two are named after their discoverers. So now we will see what is this Mandelbrot set, because that forms the basis of fractal theory. So this Mandelbrot set is a set on a complex plane. All right. So now to build the Mandelbrot set, we have to make use of an algorithm, and this algorithm will have to be used over and over again, repeatedly used. Okay, that's why it's called as a recursive formula. Only when you use it repeatedly, then the concept of self-similarity comes in. Okay, so in the recursive formula, Zn is equal to Zn minus 1 the whole square plus C. So this is going to be the formula that will be used. And the separating the points in the complex plane, using this Mandelbrot set, you can actually split the complex plane into two categories. That is, the points which come inside the Mandelbrot set and the points which are not the elements of the Mandelbrot set. And here, this is the Mandelbrot set. The one which is colored in black is called as the Mandelbrot set. Now we'll see how to construct the Mandelbrot set. So the first one is, you will have to take a point C on a complex plane. And then if it is in the complex plane, it should be a complex number. I told you a complex number is of the form A plus IB. All right. Then after that, you will have to frame the function, which has to be repeated on and off. Okay. So here you will have Z1 is equal to Z0 the whole square plus C. You know Z0 is going to be the initial value, and therefore we start with 0. So when you substitute 0 there, you get the value of C. And assign that value of C to Z1, you get the value of Z1 as C squared plus C. Yes or no? Can you see?
Yes, ma'am.
Put Z is equal to 0, and then you get the value of C. Substitute it here, you get Z1 to be equal to C squared plus C. That is again a complex number. Now what you have to do is, whatever you've assigned here, you will have to reassign and repeat the process again and again. So what happens here is, the point which was there at 0 has started migrating. Migrating meaning, or a distance move aite irukum. Enga move agudhu appadina complex plane la. The migration of the initial point across the plane. So what happens if you're going to repeat it infinite number of times, or if you're going to repeat the same iteration? Two things can happen. Okay, one is it will belong, all the points will belong to the Mandelbrot set, or otherwise it doesn't belong to the Mandelbrot set. If it doesn't belong to the Mandelbrot set, then it goes away from it. அவேனா அந்த காம்ப்ளெக்ஸ் பிளேன்ல அப்புறம் வெளியில போயிடுது. அந்த Mandelbrot set உனக்கு ஞாபகம் இருக்கும்னு நினைக்கிறேன், அந்த black கலர்ல காமிச்சது. Okay, so it will be away. All right. So here, if to explain this, let us imagine that all the points on the plane are attracted by two things. One is infinity in the complex plane, and the Mandelbrot set. So here, this Mandelbrot set divides the complex plane as the points which are far from the Mandelbrot set, they move rapidly towards infinity. The points which are close to the Mandelbrot set escape slowly. Ad meduvada infinity ku pogum. Ana points inside the Mandelbrot set will never escape to infinity. If I இங்க இருக்கிற செட்டுக்குள்ளார, இந்த Mandelbrot செட்டுக்குள்ளார இருக்கிற points, they are they don't go to infinity. But Mandelbrotோட க்ளோசரா இந்த இடத்துல எல்லாம் இருக்கிற பாயிண்ட்ஸ், காம்ப்ளெக்ஸ் பாயிண்ட்ஸ் என்ன ஆகும் அப்படின்னா, கொஞ்சம் டைம் எடுத்து இங்க எங்கேயோ இருக்கிற இன்ஃபினிட்டிக்கு போகும். ஆனா இந்த செட்டுக்கு வெளியில, Mandelbrot செட்டுக்கு வெளியில இருக்கிற பாயிண்ட்ஸ், they are very easy to reach infinity. This is the concept that you have to understand. Now, why this Mandelbrot set is important? It is important because of these properties. Enna property? Number one, Mandelbrot set is connected. So I think you know the definition of connectedness, that whenever you take any 2 points in a set, you will always be able to pass through it, or you will always have a path between any 2 points. All right. And that path also should be in the set. ஒரு செட்டுக்குள்ள 2 பாயிண்ட்ஸ் எடுத்துக்கிறீங்க, அந்த பாயிண்ட்ல இருந்து இன்னொரு பாயிண்ட்டுக்கு நீனால போக முடியணும். ஆல்ரைட். அந்த போகிற அந்த வழியை தான் நம்ம பாத்துன்னு சொல்றோம். பாத்துனா என்ன இருக்கும்? நம்ம கண்டிப்பா லைன்ஸோ ஏதோ ஒண்ணுதான் நம்ம பண்ண போறோம். If you learn graph theory, you will know about a cycle, a walk and all these things. அது எல்லாமே திருப்பியும் அதே செட்டுக்குள்ளார இருக்கு, அந்த பாத் எல்லாமே அதே செட்ல இருக்கு அப்படின்னு சொன்னா அந்த செட் வந்து Mandelbrot செட். அது ஒரு ப்ராப்பர்ட்டி, இம்பார்ட்டன்ட் ப்ராப்பர்ட்டி. அடுத்தது முக்கியமானது என்ன அப்படின்னா, ஏரியா ஆஃப் த செட் இஸ் ஃபைனட். நீங்க அந்த பிரிட்டனோட கோஸ்ட் லைனை பார்த்துக்கோங்க. ஏரியா ஆஃப் பிரிட்டன் கண்டிப்பா ஃபைனட்டா தான் இருக்கணும். ஏரியா ஆஃப் த செட்ங்கிறது இப்ப நான் பிரிட்டன் எடுத்துக்கிறேன். ஸோ ஏரியா ஆஃப் த செட் இஸ் ஃபைனட், பட் the length, over length பாத்தீங்கன்னா it would go on to infinity, which is never possible, but it is possible in fractal theory. The area of the set is finite, but its length, the area is enclosed by the length or the perimeter of anything. So on the length வந்து infinite ஆ இருக்கு. See how beautiful it is. That's why it's given the word a fascinating dimension, right? And then if we take smaller parts எடுத்துட்டாலும், அப்போ பெருசு எடுத்தாதான் அப்படி இன்ஃபைனட்டா அப்படின்னு கேட்டா இல்ல. சின்ன பார்ட்ஸ் எடுத்துட்டா கூட அந்த ஏரியா ஃபைனட்டா இருக்கும். ஆனா அந்த சின்ன பாத்தோட லெங்த் போய்கிட்டே இருக்கும். It will reach infinity. All right. So it will also be infinite. This means that the border of the sets have infinite details, and we will never find a place where the border is smooth or it is of finite length. And then the fractal dimension, I told you, will be a dimension which is larger than 2 but smaller than 3. So I told you there are 2 special fractals. One is because of the complex numbers, and the other one was iterated function system. So now going on to the iterated function system, you will have 3 plane transformations. எப்பவுமே வந்து டிரான்ஸ்ஃபர்மேஷன் ஒன்னிலிருந்து இன்னொன்னு மாறணும்னா இந்த 3 பேசிக் திங்ஸ் வழியா தான் மாற முடியும். ஒன்னு என்னதான் ஸ்கேலிங், இன்னொன்னு வந்து டிஸ்லொகேஷன், இன்னொன்னு ரொட்டேஷன். இந்த 3 இருந்தா மட்டும்தான் you can transform any object from one place to another. All right. So using these simple transformations, now we are going to form fractals. So creating an IFS fractal will have the following steps. Number 1, you will define a plane or a set of plane transformations. Then you draw an initial pattern on the plane. The pattern can be of your choice. And then transform the initial pattern using the transformations which was defined in the first step. Okay. Excuse me. And then transform the new picture. Excuse me. Transform the new picture using the same set of transformations and repeat the steps, that is the 4th step, as many times as possible, and therefore you get a fractal. So in this method, the IFS method, the most famous fractals are the Sierpinski's triangle and the Von-Koch curve. So this is what is a Sierpinski's triangle. Okay, so this triangle is a fractal which is got by taking the midpoints of each of the sides of a equilateral triangle. If you could see, this is an equilateral triangle, and here they have taken the midpoints of each of the sides. These are the sides, and therefore they are taken the midpoint of each of the sides. So what we are going to do is iterate. The iteration should be repeated an infinite number of times. What is the iteration? Connecting the midpoints of each of the sides of an equilateral triangle. It is simple. ஒரு ஈக்குவலேட்டரல் ட்ரையாங்கிள் எடுக்கிறோம், அதோட மிட் பாயிண்ட், ஒவ்வொரு சைடோட மிட் பாயிண்ட் எடுக்கிறோம், அதை நம்ம கனெக்ட் பண்றோம். இதைத்தான் நம்ம இன்ஃபினிட்டா செஞ்சுக்கிட்டே இருக்க போறோம். இதை செஞ்சுக்கிட்டே இருக்கும்போது see the next one. See, now when you do this, you get 3 different triangles. Again, this triangle is an equilateral triangle. Repeat the process. What is the process? Take the midpoints of each of these triangles. Of this triangle, join it, you get this. Again, this is an equilateral triangle. Take the midpoints, join, you get another. So this one triangle is now transformed into 3. Now this one, smaller one, is now again transformed into 3. And again, this is now into 3. And similarly, you keep on repeating. This is how you get. Either you can start make repetitions. Am I fast? Am I fast? Or are you able to understand? Are you able to understand?
Yes, ma'am, we can follow.
Okay, thank you. So here, this is how we construct the Sierpinski's triangle. So this is an equilateral triangle. You start with an equilateral triangle, connect the midpoints of each side of the triangle. So these are the midpoints of the triangle. You connect it. They form 4 separate triangles. See, 1, 2, 3, and 4. So now you're going to cut out this triangle in the center so that you get an image which is beautiful for you. All right. So cut out the triangle in the center. Now what you're going to do is repeat all these 3 steps. Repeat steps 1, 2, and 3. So here you are left with 3 triangles. Again, do the same thing. The center triangle of each of the colored one is removed. And therefore, repetition and with adequate screen resolution will give you the pattern or will give you the Sierpinski's triangle. And the dimension, we are very much interested in finding the dimension of a fractal object. Okay, as I told you, if you remember, the dimension of a fractal object is going to be non-integer. See, this is a non-integer. All right. So how do we find out? So as told earlier, the formula is d is equal to log n divided by log s, where the scaling is 2. So here, if you could see, this side is divided into 2, 1 and 2. Okay, the scaling is 2. So this side also, it has been divided into 1 and 2. Okay, so the scaling is 2. And when you do that scaling, the number of similar pieces that you get is 3. I told you that you get 3 equilateral triangles. So it is going to be log 3 divided by log 2, which is 1.584. And this is a non-integer number. And this is what is called as the fractional dimension or the Hausdorff dimension. And again, you can also do with or construct the Von-Koch curve. So this Von-Koch curve is generated by a simple geometric procedure, which can be iterated infinite number of times. And this curve divides a straight line segment. It is a straight line. You could see this is a straight line segment. And this straight line segment is divided into 3 equal parts. And then the intermediate 3 equal parts. And the intermediate part is again replaced by 2 segments of the same length. And repeating this procedure, you get the Von-Koch curve. So going on to the construction of it, you have a straight line here. The straight line is now divided into 3 parts. Say 1, 2, and then 3. Okay, equal parts. And then the center part of it is now given an elevation. Okay, it's given, it is divided into 2 with one angle as 60 and the other angle is 120. So you get a figure like this. Now what they do is, now see, you have 1, 2, 3, 4. 4 line segments similar to this. They are smaller parts of the larger one. Apply the same thing. What happens? Divide this part into the 3 parts, then elevate the center portion of it. So you get a portion like this. Similarly, this can be done. This also can be done. And this also can be done. And again, this smaller part is similar to the larger one. Again, repeat the procedure. You get this figure. Again, here, repeat this procedure, you get this, and it goes on and on. So when it goes on and on, this is how you get. Can you see this figure? There are so many identical patterns. The same thing, when you repeat again and again, this is the pattern that you get. But we want to see about the dimension. Using the dimension, we can check whether it is a Euclidean shape or it obeys Euclidean geometry or fractal geometry. So here again, for the dimension, it is log n by log s, where s is that the scaling part. That is the line was divided into 3 equal parts. So 3, and then the identical parts were 4. So when you take the log, it is approximately equal to 1.261. But remember, when it was a line, what was the dimension of a line? Do you remember the dimension of a line which I told you earlier? 1. But same line, when you apply a particular recursion or you do some procedure on and on, you get a fractional you get a fractional number, which is a non-integer. All right. Now, see, this is how the fractals are. The computer graphics have made this beautiful. So the original figure is this, and from there you can get smaller, similar original pictures. Okay, isn't it beautiful? All right. Now, if you want to know about the importance of something, you will have to know where it is applied. Application தெரிஞ்சா மட்டும்தான் ஒரு subject எவ்வளவு important அப்படிங்கிறது நமக்கு தெரியும். So now we will see how these fractals are omnipotent in nature. Nature is full of fractals. Okay, so because here anything that appears random and irregular can be a fractal. Fractal describes all complex natural processes. Okay, and those processes can be visualized by computers nowadays. And fractals form an integral part of lives which appear as tiny as the membrane of a cell. Nama body kulla irukra cell fractal da. That is also a fractal image, and it can go up to the majestic solar system. கேலக்சியும் ஒரு ஃப்ராக்டல் தான். நம்ம உடம்புக்குள்ள இருக்கிற செல் ரொம்ப சின்னது, அதுவும் ஃப்ராக்டல் ஸ்ட்ரக்சர்ல தான் இருக்கு. இந்த கேலக்சி, இந்த யூனிவர்ஸ்ல இருக்கிற கேலக்சியும் ஃப்ராக்டல் ஸ்ட்ரக்சர். ஸோ ஃப்ராக்டல்ஸ் ஆர் யூனிக் irregular patterns left behind by unpredictable movements of the chaotic world. So chaotic அப்படின்னு சொன்னா confusion அப்படின்னு சொன்னா like there is a sort of indeterminate character inside nature. Alright, so எல்லாமே வந்து அன்பிரடிக்டபிளா தான் இருக்கும் வேர்ல்ட்ல. இந்த ஃப்ராக்டல் தியரி ஆக்சுவலி இன்னொரு பெரிய ஒரு பிரான்ச்சுக்கே கொண்டு போய் விடும், which is called as the chaotic theory. Okay, and all this you will not know now because most of you are in the UG, I think. So whenever you go in for research, you can go in for all this. So the world is full of fractals, and fractals you can see in the branching of a tree, the leaves of a tree, the structure of the tracheal tubes inside the human body, the veins, the DNA molecule, the flow of fluids or the movement of water currents in the ocean. Even in stock market, you cannot predict. Okay, nothing is smooth there. Stock market, in nature, the cloud and the galaxy. Now, the application of fractals, the fractals can be applied in any field, in any, or you can say many scientific fields. That is, they are able to, the only, the beauty of this fractal is all the structures, all irregular structures can be identified or modeled. It can be modeled using fractals, and you can apply the principles of fractal geometry to decompose it into smaller patterns, because you learned about self-similarity. So chinna pattern padichitale nammala periya pattern ku you can predict it. Okay, the future behavior you can predict. So it is very much useful in modeling natural phenomena. And when I say this, it can be used to study climate changes, detect cancerous growth. You can also know about the geological process that is breaking up of rocks, glaciers, and all those things in medicine and even in weather forecasting. So here you can see how fractals are used in medicine. All of us know that this is the heart, okay? The human heart beats regularly. Only if there's a beating in the heart, we'll be alive, all right? So this beating, most of us till now, we were thinking it is regular and linear. It is linearly beating. But recent studies have shown that it follows a fractal pattern. It is not regular. It is a little bit, there is a little bit of irregularity in the beating of the heart. And the irregularity, concha changes, minor alterations in those fractal scales is the only cause for the cardiac arrest. And moving on to the lungs, in the lungs, you can explain the gaseous exchange in the lungs. And this is now the booming one because for COVID, lungs is what is அதோட ஃபங்க்ஷன் தான் இப்போ ப்ராமினென்ட்டாக நம்ம பார்த்துட்டு இருக்கிறது. ஸோ யூ கேன் ஆல்சோ யூஸ் ஃப்ராக்டல் தியோரி டு மாடல் த lungs. Okay, and then in biosensor interactions also you can use fractals. Now, fractals can be a tool to study weather forecasting, ecology, nature, and environment. And here with fractal geometry, I told you that you can model anything in nature. For example, weather. Weather forecasts are never totally accurate. எப்பவுமே ஒன்று சொன்னாங்கன்னா நம்ம டிவியில் சொல்லுவாங்க இன்னைக்கு மழை கண்டிப்பாக வரும், உடனே சொல்லுவாங்க சொன்னாங்களே வரலையே, அப்போ அவங்க சொன்னது தப்பா? இல்லை, இட் இஸ் நாட். அவங்க சொன்னது தப்பு கிடையாது, பட் அது மாறுறதுக்கு சான்சஸ் இருக்கு. ஏன் மாறுது அப்படின்னு சொன்னா பிகாஸ் ஆஃப் ஃப்ராக்டல்ஸ், பிகாஸ் ஆஃப் தி மைனர் டிஸ்டர்பன்சஸ், வெரி ஸ்மால் disturbances in the airflow, solar heating, etc. Okay, so this minor disturbance, however minor it is, that will create a change. And create a change na epdina, it will increase geometrically with passage of time. As time moves on, the small change goes on geometrically increasing, and that is why what was told in the TVs or whatever it is, that is not true. All that is because of this fractal nature of the climate or the environment. And fractals are very useful in detecting earthquakes, and you can also analyze its pattern, the seismic patterns of the earthquakes. And you can also model soil erosion, mineral fragmentation, and the behavior. Even parada or pakkathila irundhu innoru pakkam pogudunna, what is actually idha neenga vanda the butterfly effect. This is what you could relate it to, the butterfly effect. எங்கேயோ ஏதோ நடந்தா இன்னொரு பக்கம் ஒரு வைப்ரேஷன் இருக்குன்னு சொல்றாங்களே, all this is because of this. And then in ecology, this fractal study can be used to quantify the amount of carbon dioxide which can be processed by forest எந்த அளவுக்கு ஒரு பர்டிகுலர் ஃபாரஸ்ட் எந்த அளவுக்கு கார்பன் டை ஆக்சைடை ப்ராசஸ் பண்ணி நமக்கு ஆக்சிஜன் கொடுக்கும் அப்படிங்கிறதையும் நம்மளால ஸ்டடி பண்ண முடியும். And we can also study the spread of forest fires. And then in computer science, this fractal theory is used in image compression. For example, we can compress our images to very small size by using this JPEG format or the GIF file formats. So this is because of the application of fractal models there. And you also have applications in fluid mechanics where you can study the vibration in the flow of fluids or the turbulence. And this is where the chaotic theory and all moves on. And then in petroleum science also you can use this. And in physics also, you can study the roughness of surfaces. Moving on to astronomy and telecommunications, this fractal theory is used to study the curvature of space-time. The rings of the Saturn oda rings kuda nammanaala analyze panna mudiyudhu, galaxies analyze panna mudiyudhu. And astrophysics la in the fractal theory use panni da formation of stars they study. And why do they use this? Because the galaxy is fully irregular. It is highly irregular and they are self-similar to each other. And when we talk about telecommunication, fractals finds an important place because nowadays the antennas and the wireless devices are modeled using fractal concept. இதுல என்ன பண்றாங்கன்னா அந்த ஆண்டனாவோ இல்ல வயர்லெஸ் டிவைஸோட சைஸ் ரெடியூஸ் பண்ணிடுறாங்க. யூசிங் தி கான்செப்ட் ஆஃப் ஃப்ராக்டல் தியரி, they reduce the size and the weight, but then they increase. When the size reduces and the weight reduces, that naturally increases or widens the frequency and its efficiency. All right. And you can also see that fractals are used in chemistry. I remember I told you that it is useful in studying the DNA patterns because these are all DNAs and each DNA is similar to the other one. All right. So it is also used in in chemistry. Then in robots, in robotics, this fractal robot is an object made up of cubic bricks. Bricks meaning not literal bricks, a block. We're having some electronics embedded in it. And when you reconfigure themselves, இதை இன்னும் கொஞ்சம் ரீகன்ஃபிகர் பண்ணும்போது அதை ரீகன்ஃபிகர் எப்படி பண்ணலாம்னா கம்ப்யூட்டர் சிஸ்டம் யூஸ் பண்ணி பண்ணலாம். வேர் இஸ் இட் இம்பார்ட்டன்ட் அப்படின்னா மைனர் சர்ஜரிஸ் நம்ம பண்ணணும் அப்படிங்கிற போது யூ கேன் இன்சர்ட். இட் இஸ் ஆஃப் 1 mm size. These robots are of 1 mm size and you can insert it anywhere. And another important quality is this robot can change its shape depending on the object in which it is inserted. எந்த இடத்துல இருக்கோ அதுக்கு தகுந்த மாதிரி இந்த ரோபோட் வந்து it can change its shape and therefore it's very useful. And finally, we also see fractals in arts, cinema, graphic designing, and then in architecture. It did not leave any field of life. Fractals எல்லா இடத்துலயுமே ஒரு தனி ஒரு இடம் பிடிச்சு வச்சிருக்கு. Okay, so this technique here gives rise to software programs now widely used across for creating special effects, like Genesis planet sequence in Star Trek and the Wrath of Khan and the Return of Jedi. இது இந்த இடத்துல எல்லாமே ரொம்ப யூஸ் பண்ணியிருக்கிறது என்னன்னா fractal theory. And in architecture, you can see if you can see the temple. See, each part of the temple resembles the original one. Okay, this is the Virupaksha temple at Hampi, and this is an excellent example for fractals in architecture. All right. Yes. Are you there along with me? So we are come to the end of the presentation. So the important things or the key takeaways are 2 things. Number 1, the mathematical angle, the mathematical concept of fractals. Mathematical concept of fractals is, number 1, it has self-similarity and the non-integer dimension. This is how fractals differ from the other Euclidean objects. Number 2 is the motivational angle. எங்க மேம் மோட்டிவேஷன் வந்தது? இதுல போர் தான் அடிச்சுது. கேட்டுக்கிட்டே இருந்தோம், நீங்க பாட்டுக்கு ஏதோ பேசிட்டே இருந்தீங்க. என்ன இதுல அப்படின்னா, மேத்ஸ் வந்து ஒவ்வொரு பார்ட்லயுமே நமக்கு ஏதோ ஒரு மெசேஜ் சொல்லிட்டே இருக்கும். என்ன மெசேஜ் அப்படின்னா, இதான் மெசேஜ். Convert your obstacles into opportunities. And if you do that, it will always be a breakthrough. ஒரு திருப்பு முனையா தான் இருக்கும். And அது அந்த மாதிரி செய்யும் போது நீ ஒன்றும் பெருசா செய்ய தேவையில்லை, புதுசா ஒன்று கண்டுபிடிக்க தேவையில்லை. See, your innovation cell in your college will talk about doing things new in a better way, in a different way. அது என்னவோ பெருசுன்னு நம்ம நினைச்சுக்க வேண்டாம். கன்வென்ஷனலா என்ன செய்யறோமோ, ட்ரெடிஷ்னலா நம்ம என்ன செய்யறோமோ, அதிலிருந்து ஒரு சின்ன ஹைக், ஒரு ஸ்லைட் வேரியேஷன் கொடுத்தாலே போதும். that becomes an innovation. So in the obstacles into opportunities in பார்க்கும்போது, I told you about complex number system. So complex number system அப்படிங்கிற போது அங்க வந்து usually mathematicians என்ன பண்ணாங்கன்னா, they used to find out the square root of numbers, positive numbers. It was very easy to find out the square root of positive numbers. But there was one point of time where they had to find out the square root of -1, negative number. அப்ப அதுக்கு ஒரு ஆன்சர் இல்லாமலே இருந்துச்சு. அந்த ஆன்சர் இல்லாம இருந்து எத்தனையோ பேர் அதுக்கு மேல அது ப்ரொசீட் பண்ணாம போயிருக்கலாம். ஆனா யாரோ ஒருத்தர் அதுக்கு அதை ஓவர் கம் பண்றதுக்கு ஒரே ஒரு டினாமினேஷன் தான் கொடுத்தாங்க, ஒரே ஒரு நோட்டேஷன் தான் கொடுத்தாங்க. அதுக்கு நோட்டேஷன் ஐன்னு கொடுத்தாங்க, இமேஜினரி பார்ட். இப்ப அந்த இமேஜினரி பார்ட் ஒரு நம்பர் கூட அட்டாச் ஆனனால ஒரு வாஸ்ட் சப்ஜெக்டே நமக்கு இன்னைக்கு வந்துருக்கு, காம்ப்ளெக்ஸ் அனாலிசிஸ். அண்ட் தட் காம்ப்ளெக்ஸ் அனாலிசிஸ் இஸ் வைட்லி அப்ளைட் எவ்ரிவேர். ஆல்ரைட், அதே மாதிரி தான் இங்க ஃப்ராக்டலும். எல்லாரும் என்ன கன்வென்ஷனலா யூக்ளிடியன் ஜியாமெட்ரியில என்ன பண்ணிட்டு இருந்தாங்க, இன்டீஜர் நம்பர் தான் டைமென்ஷனா வரணும் அப்படின்னு எல்லாரும் மனசுல நினைச்சிட்டு இருந்தாங்க. ஆனா ஏதோ ஒரு இடத்துல யாரோ ஒருத்தருக்கு அது நான் இன்டீஜர் நம்பரா வந்திருக்கும். அதுல ஒரு சில பேர் ஐயோ இது வரக்கூடாதே, நம்ம தப்பு செஞ்சுட்டோமோ அப்படின்னு விட்டுருப்பாங்க. ஒரு சில பேர், அந்த ஒரு சில பேரையும் the பெஸ்ட் பர்சன் அவங்கதான் அதை கண்டுபிடிச்சிருப்பாங்க. அப்ப இப்படியும் இருக்கு, அப்ப லைஃப்ல நிறைய இந்த மாதிரிதாம்மா இருக்கு. And this moment where we are amidst in the COVID pandemic, all of us are some or the other way depressed. Okay, so we always see our problems as a big mountain, and I told you a mountain is a fractal. All right, so mountain பார்த்தோம்னா அப்படியே உட்கார்ந்த இடத்துலயே அதை பார்த்துட்டு அப்படியே உட்கார்ந்துருப்போம். அதை சின்ன சின்ன பீசஸா பாருங்க, சின்ன சின்ன ப்ராப்ளம்ஸா பாருங்க. பெரிய மலை போல ப்ராப்ளமா பார்க்காதீங்க, சின்ன ப்ராப்ளமா பாருங்க. டெய்லியும் keep a set of small goals. Don't go in for big goals. Keep small goals, daily goals. Achieve those goals. When you achieve every day's goals, you will be right on the top of the mountain on one particular fine day. Okay, and all the blessed, and God bless. Thank you. And thank you all the students who have been sparing your valuable time for so long. Thank you very much.
Thank you, ma'am. I have no words to say, and thank you for the magic you have created with your words and wisdom. So yeah, you're absolutely right. Max always gives us some message. So I remember one message from my friend who named Kailash. He's saying that the exponential factor is still the same. It doesn't matter you can differentiating or integrating. It's e power x is always e power x when you differentiate or integrate. So as humans, we have to stick to the same with our values, and as ma'am said, we have to achieve the goals in everyday's life so we can achieve a bigger and bigger every day. So thank you, ma'am, for the time you have been, and it's been a presentation with knowledge and wisdom. Once again, thank you. So we are at the end of the webinar. So it's a responsibility to conclude this session with so much of gratitude, because gratitude is almost a value which has to be taught and which has to be received by someone around us. So it has to be with us. So at that point, I'm inviting N. Renita to deliver the vote of thanks.
The best and beautiful things in the world cannot be seen or even touched. They must be felt by heart. Thank you is one such prayer among them. I take this opportunity to propose a vote of thanks to those who have directly and indirectly contributed their time on this webinar, Fascinating Dimensions of Nature, Fractals, organized by our department. At the outset, I thank our chief guest, resource person, Dr. Nirmala Irudayam, Assistant Professor of Mathematics, Nirmala College for Women, Coimbatore. You are really enlightened with your knowledge and presence. The points you shared was really informative. Once again, I thank you for taking out time from a busy schedule and enlightening us with the knowledge. A special thanks to our Associate Professor and Head of the Department, Dr. V. Gunasagaran, Department of Mathematics, Iterated, Staff Coordinator, Dr. K. Shendagam, Assistant Professor, PhD Gas Institution Innovation Council Member, Department of Mathematics, and all other staffs for their unflinching support. Our heartfelt thanks to our students for active participation. With these warm words and a kind message, we move to the end of today's webinar. Thank you and have a nice day.
Nirmala madam.
Yes, ma'am. Yes.
Thank you. Thank you. It was very wonderful.
Thank you,
ma'am. The presentations were very interesting, madam.
Thank you, ma'am.
I hope the students will take into mind and they will proceed to further research activities. Yes or no, students?
Yes, ma'am. We'll surely take that, ma'am.
Yes. Whatever she has given you the ideas, you have to take and